Hello, now we're on to the next section of this chapter, section 3.2. So, this one is talking a little more about polynomial functions. Let's see. It's called Polynomial Functions and Their Graphs. So we're kind of slowly building up to how to graph these things. So let's see, the intro says, pay at the pump. Other than outrage, that's kind of funny. What is going on at the gas pump? Is surging demand creating an increase in oil prices? Like all things in a free market economy, the price of a commodity is based on supply and demand. In the homework for this section, we will explore the volatility of gas prices over the past several years. So that'll be just one example of a polynomial that actually represents something in real life. So you might see that in the homework, or it'll definitely be in the book. If you look in the exercises at the end of this section. The first thing we want to do is define something you've probably seen before, but it's kind of worth looking at again. The definition of a polynomial. So a polynomial, it's a function in the variable x with degree n. Okay, so degree, remember, is basically that's the highest power. Degree equals the highest exponent. So we're just going to call the highest exponent n. Who knows what it is? It could be 1, 2, 3, 4, on and on and on. But it should look something like this, and this looks really funny and really general. But when we see some examples, I think it'll make more sense, where these guys, the a with the subscripts from this expression here, those are the coefficients of the terms. A sub n, that's the leading coefficient, because that should be the coefficient of x to the nth power, which we said is the highest degree term. Coefficient. And n is a whole number. And n is the highest power. So one thing that it doesn't mention here is that, well, it says n is a whole number, but actually all exponents should be whole numbers. All exponents should be, well, I should say 0 or whole numbers, because I think 0 is not counted in the whole numbers. I think whole numbers technically starts at 1 and then goes 2, 3, 4, 5. Okay, so it's just, there's some, I guess, some things that need to happen before we can call something a polynomial. So that's just a lot of little things to remember. But now they really want to test us on, do we really understand what is a polynomial and what isn't? Let's see, this first objective here, it says, the exponents on the variable in a polynomial must be non-negative integers. Well, actually, that's true, because non-negative integers basically means whole numbers. Because whole numbers are positive, which means non-negative. And integers are integers are 1, 2, 3, 4, 5. But also integers counts the -1, -2, negative. So the negative guys, but because they specified non-negative, I know that's just going to be the whole numbers, basically. So this would be a true statement, the one they gave me. The second one here, though, what does it say? The coefficients of the variables in a polynomial function must be non-negative integers. Well, notice in the definition it didn't say anything about that. What it did say, though, is that these coefficients, which they're just calling a sub I, which, and this looks kind of funny, but this means coefficients must be real numbers. So they didn't say that they have to be non-negative integers. They said they have to be real numbers. And real numbers is almost as broad as it gets. Real numbers is everything that except for imaginary. So this would be false, because the coefficients, they're not that strict about coefficients. In order to be a polynomial, the powers have to be whole numbers, but the coefficients don't have to be. They can be, I can even have like the square root of 5 as a coefficient. That's fine. I can have fractions. I can have decimals. I can have whatever I want, negative, positive. It's only the exponents that have to be whole numbers. So it's just something to keep in mind, I guess, just so you can recognize what is a polynomial and what isn't. And then the next objective here is to recognize characteristics of graphs of polynomial functions. The first problem that we're looking at, it says, the graph of a polynomial function may have a sharp corner. Well, I think these are supposed to be true or false also. I'm sorry. I should say, I don't know if it doesn't say, huh? These are all true or false. And this problem, I kind of look at this one and I'm kind of wondering why they even put this here, because we don't know what the graphs of polynomial functions look like yet, unless you've already taken this class or a similar class. So how would I know if they have sharp corners or not? So this one I think is just more of a preview sort of what we're going to see. But what we'll see is basically polynomial functions will take on one of these four forms. They'll look like one of these four depending on what you're given. So let's just kind of take a look at them and then we'll decide whether they can have sharp corners or not. So let's see, just so we know. Like I said, you shouldn't necessarily have known this before. I don't know how they expect people to know that if this is true or false or not. All polynomials have a graph like one of the following. So one of these four guys. So it could look like kind of a parabola, but a lot of times if the polynomial is more complicated, it might have some little wiggles in it like that, you know? So, but it's basically a parabola shape. It just kind of has wiggles. But you could also have an upside down parabola type shape with a few wiggles in it, something like that. That could be possible. Or like a cubic shape, so like the graph of x cubed, but it might also have some wiggles. And then also it could be that reflected across the y-axis, so something like this. And let's just throw in a few more wiggles just for fun. That's what makes polynomials kind of interesting, is that their graphs look a lot like either a parabola or a cubic, except they're going to have some wiggles in the middle, which is, it's our job to figure out what those wiggles look like. And we'll nail that down in the next objective, kind of when do you know which of these four graphs that you're looking at for your polynomial. So based on those graphs, let me answer this question here. It says, the graph of a polynomial function may have a sharp corner. Well, it looks like based on those four graphs, that would be false. These all look like they have smooth, kind of curvy shapes. I don't see any corners there. So that's, I guess, something to keep in mind. So if you're ever graphing a polynomial, try not to draw any corners or else you know you did something wrong. In polynomial graphs. Yeah, alright, and what else did they have for us? Hopefully this is something we can actually answer. The graph of a polynomial function may have a gap or a break. Well, if you look at these guys, the four that we drew, there are no gaps or breaks. It's like, as soon as I started drawing it, I never lifted my pen or pencil from the paper as I was going through it until the very end. So that would also be a false. False. Because polynomials are always continuous, is probably the reasoning I would give. Polynomials are always continuous. Alright, next objective is to determine end behavior. And I'm sorry, this little table here is kind of not beautiful looking, but end behavior, okay, if you look at those four graphs that I drew up above here, so notice the very first one has, end behavior is like where it goes eventually, I guess. So the very left one here, both ends go up, so it's like goes up on both sides. So that's one possible end behavior, they call it. The second one from the left, it looks like it's going down on both sides. The arrows are both pointing down. Down on both sides. Okay, that's another possibility. And then the next one, it looks like it goes down on the left and up on the right. So I mean, we mentioned that we see the wiggles in the middle. We do care about those, but just the term end behavior only talks about what happens at the end. Which way are the arrows going? So this third one from the left goes down on the right, up on the left. And then the very last ones, I guess the only thing we're missing is that it goes up on the left and down on the right. Goes up on the left, down on the right. Alright, so that kind of hopefully gives us an idea of what's going on. So this will really narrow it down here. It says the end behavior of a polynomial function, and I guess this is kind of giving you a guideline to tell you, based on the specific polynomial function you're given in an example, which of those four graphs will it look like, basically? Which, will it be going down on the left, up on the right? Will it be going up on the right, down on the left? Or, I don't know, was that the same thing? Vice versa, both up, both down. Okay, so notice though, the top two, the degree is odd. And remember, degree we said was the highest powered exponent. So if the degree is odd, it's going to look like a cubic shape, basically, except maybe some wiggles. And by cubic shape, I mean like the graph of y equals x cubed. Something like that. It might wiggle in the middle, but it's pretty much going to look like that. So it's one thing that narrows it down, but then if you had even degree, so the highest power in your polynomial is an even number, then it's going to be based kind of like a parabola, except for some wiggles in the middle, like we said. Parabola shaped. Yeah. And then kind of like with parabolas and with cubics, you can tell whether it's going to be going up on the right, down on the left, or up on the left, down on the right, based on the leading term. So remember, if you have y equals x cubed, that graph we memorized, it goes down on the left and up on the right. But if you were to throw a negative in front of the x cubed, now all of a sudden it's a reflection across either the x-axis or the y-axis, however you want to think of it. So that's how you would know. It's normally a cubic looks like this guy, the top left graph. But if I were to throw a negative in front of it, as it says here, then it would go up on the left, down on the right. And then similarly with the parabola type shapes, let's see here. If you have y equals x squared, if the leading coefficient is positive, like we're used to with y equals x squared, a regular parabola with no negatives goes upward. It's an upward parabola. But if the leading coefficient is negative, like if you put a negative in front of x squared, then it's going to be a downward parabola. So that's kind of how you narrow down which of the four graphs it's going to look like. So let's try it here. Actually, they kind of have this one done for us, but that's okay. They want us to use the leading coefficient test, which is pretty much what we wrote up here, this little box that has all the graphs. Use the leading coefficient test to determine the end behavior of the graph of each function. So first, this guy. Okay, so first of all, it kind of already has the answer written, but I'm just going to go through it anyway. The degree of this guy is 4, because that's the highest power. That's an even number. So it's either going to be, the upward facing parabola type shape or the downward. So it's one of those, but the leading coefficient will narrow it down and tell me which one of those it is. The leading coefficient, that's the coefficient of the highest powered term, so the coefficient of x to the 4th would be 1. That's a positive number. So that helps me narrow it down. I know it's going to be an upward parabola. Because a downward parabola would have me have, what's it called? A negative in front of the x to the 4th term. So that's your answer. It'll be the graph rises to the left and rises to the right. That's what you could say. Or you could say it goes up on the right, up on the left, as long as you get your point across somehow. Alright, let's try that same thing, but a new problem here. So looking at this guy, I see the highest powered term is 5x to the 3rd. So the degree is 3. So that narrows it down to, it's going to be some kind of cubic shape. It'll either be this type of guy or that type of guy. One of those two. But the leading coefficient, whether it's positive or negative, will really narrow it down to one of those two. The leading coefficient is the coefficient of the highest powered term, so 5. That's a positive number, so I know it's going to look more like the graph of x cubed, no reflections or anything like that. So it must be this guy here. This is the graph of y equals x cubed. The other one is the graph of a negative y equals x cubed. So I'd say it falls, or it's going down. Or sometimes I think, using the language that they're using, it falls on the left, up, or rises on the right. Kind of depending what language you want to use. But that's how I would describe the end behavior. Now this next one's, the function's already factored for us, or this polynomial's kind of factored. Which would be nice if we were actually trying to do something algebraically with this function, I guess, but since we're not really trying to do anything algebraically, we're just trying to figure out the degree and the leading coefficient. It's actually kind of making it a little harder. Because it looks kind of like, okay, I see a 3rd power, that looks like the highest power I see. But imagine if you were to multiply this whole thing out. What if I multiplied this out? Okay, and I'm going to do it, but only this one time, and then I think we'll be able to kind of extrapolate sort of what happens here and then never have to do it again. So for now, I'm going to leave that 2x to the third out in the front, but I'm going to FOIL this part out, the x minus 1 times x plus 5. If I FOIL that out, I get x squared plus 5x minus 1x minus 5. See, and if I combine like terms, I get x squared plus 4x minus 5. And now I'll distribute that 2x to the third. Let's see, that'll be 2x to the fifth plus 8x to the fourth minus 10x to the third. So now I see the degree is actually higher than it looked like it was to begin with. The degree is 5 because that's the highest powered term. So, you know, I mean, we did that, but that would be a pain to have to do that every time. So I think we'll just kind of make the statement that if you have it in its factored form like this, what you can do is just add all the powers of x. So here's a third power. There's an, invisible 1 power on x here, and invisible 1 power on x here. So that's kind of a quicker way to do it if you don't want to multiply it all out. So I'm going to say if the polynomial is factored, add all exponents on x to determine the degree. And that should always work. You don't really have to multiply it out. So I'm going to go, okay, it was a third power plus, there was another x that had a 1 power and a final x that also had a 1 power. That's how we would have gotten 5 if we didn't really want to multiply it out. We didn't have to. So anyway, the degree is 5. That means it's either going to have n behavior looking like this or like this. That's really what we're asking here. But it all depends on the leading coefficient. So when I multiplied it all out, I noticed the leading coefficient didn't change. So the leading coefficient was positive 2. Positive, that's a positive number, of course, which means it's going to be the cubic shape on the left, the kind of normal x cubed shape. So it was, you know, it was clear to me what the leading coefficient was, and that was because we multiplied it out. But if you didn't want to multiply it out, you know, you wanted to leave it in its factored form like this, because that's kind of, a lot of times it's a lot of work to multiply it out. So if you did want to find the leading coefficient, what you would do is multiply all the coefficients of x. So this was a 2 times a 1 times a 1 here, which is 2. So and then I'll say and multiply all coefficients of x to find the leading coefficient. Multiply all coefficients of x, to find the leading coefficient. I mean, you won't come across this type of thing too often, but let's just give you a quick way of doing it instead of having to multiply it out. That would be a pain. So here we go. This is a good one. Let's try this out. This one I could multiply it all out and then do the same thing, but I'm just going to say the degree is going to be all the exponents added together. The 2 plus this x has an invisible 1 power, and this last x also has an invisible 1 power. And if I add those together, of course, I get 4. So I have a 4th degree, which means it's either going to be some sort of parabola shape, so it's up on the left and up on the right, or it's down on the left and down on the right. I'm kind of not sure which one yet, but now I can figure it out by saying that the leading coefficient, it's going to be all the coefficients of x multiplied together. So the x squared has a coefficient of -1. This x only has a 1 in front of it, and so does this x. Invisible ones. But that product is -1. Since that's a negative, that means that this graph is going to be kind of the downward facing type. So it's down on the left and down on the right. Down, or yeah, their language if you want to use that. I just write falling because if they use that language, then you'll recognize that it means the same thing as down. And then down, or falling on the right. And I think we forgot to put that language for the last one. This last one we decided it was down on the left, down, falling on the left, because that's the highlighted graph right there that we decided it was, and up or rising on the right. Alright, looks good. So end behavior, that's pretty important. That'll help us kind of picture the graph of these parabolas. But the next important step is we kind of want to tackle those wiggles. How do you know where the wiggles are when you graph these things, and where do they occur and all that type of stuff? So let's see. Let's see. And how we'll do it is, like, if let's say I graph, or I know that a certain polynomial has a graph that looks like, let's see, I'm just going to make one up. It goes, sure. Well, kind of those wiggles, I could probably narrow them down if I knew the x-intercepts, because I would have to cross the x-axis here, 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 here. So that might kind of tell me how those wiggles look, you know, how many times it crosses the x-axis. So that's our next objective, is to be able to find the x-intercepts. How to? Well, that's what we're going to do now. So I guess another word for it, I'm not sure why they name it again, but in polynomials they call x-intercepts zeros. I don't know why. Zeros are the x-intercepts of polynomials. Yeah, I don't know why they don't just call them x-intercepts. They're just trying to confuse us, you know. They like that, math people. Yeah. Okay. So if you remember, we saw x-intercepts, I think, when we were talking about graphing parabolas. But to find x-intercepts, let's see, to find x-intercepts, if you remember, we let y or f of x equals 0, whichever one you have, and then solve for x, and solve for x. So let's try that. The function we're given here is x cubed plus 2x squared minus 4x minus 8. We'll set that equal to 0. Oops. Well, you could set it equal to 0 on either side, of course. But this is where you have to be good at factoring, because there was, you know, when you learn how to factor, there were a lot of factoring techniques. But the one that worked for when you have 4 terms in your polynomial should be, what's it called? Factor by grouping. So we need to factor by grouping. There we go. Alright, which means you're going to split it down the middle, kind of group the first 2 terms together and then the third and fourth terms together. So I'm going to look at first right now the first and the second terms, just those guys. What's the most that they have in common? I'll take that out. So they have an x squared in common. If I factor an x squared out, x plus 2 is left. And now I do the same thing for the third and the fourth term. What do the third and the fourth term have in common? Well, they have a 4 in common, but they're both negative. Actually, whatever the sign in the middle is, so let's say, if this is a negative, I want to factor a negative out. If that's a positive, I want to factor a positive out. So those highlighted signs should agree with each other. And then let's see, negative 4 times x would be negative 4x, and negative 4 times positive 2 would actually be negative 8. And now this is a good sign. Now I have the things in my parentheses are exactly the same. That's how it should be if you're doing this right. So the answer will be, or, you know, the factored form will be x plus 2, because that's what they have in common. But then kind of the leftovers are x squared minus 4, and those come from, let's see, the parts that were factored out of the 2 terms, the x squared and the minus 4. But now that I look at this, I'm kind of thinking, you know what? It's x plus 2, but this is actually, the x squared minus 4 is a difference of squares. You can factor that further. That's just a different factoring technique that we're supposed to know at this point. Difference of, squares. So that might not be, if you're not familiar with that, it might not be a bad idea to Google it. But yeah, x squared minus 4 factors into x minus 2, x plus 2, or vice versa. So this, it used to look like x squared minus 4, but now I've converted it into x minus 2, x plus 2. Okay, and now what we're supposed to do to solve this all the way is, as it says here, apply the zero product principle, which just says if you have 2 things multiplied together like this, a times b, they're just being general here. If you have 2 things multiplied together and you get 0, then one of those should be 0. So that means in my equation, or the equation I'm trying to solve, x plus 2, x minus 2, x plus 2, all those multiplied equals 0. That means I should be able to set each of those factors equal to 0 and solve for x. And that's a solution to this equation. So that's all I'm doing here, is taking whatever's in each factor and setting it equal to 0. And then I'll try to solve each one individually. This one I'll solve by subtracting 2. So there's 1. one answer. And this one I'll solve by adding 2. There's another answer. The last one, though, it's like a repeat. I already had this answer. So that means there are 2 x-intercepts. It looks like there are 3 because I found 3 solutions, but 2 of them were the same, so it's kind of like I wasted time trying to find the same thing I already found. X equals -2, and x equals +2. However, the fact that that one x-intercept occurred twice, you know, it was here and here, that will be significant as far as the graph goes, but we don't know yet what that means. We want, you know, we want to take it one step at a time, but that will be important. Yeah, when you have one x-intercept occurring more than once like that, that means something. So let's try that one more time. That's, you know, kind of a good review of factoring. So this is a new polynomial. We're going to set f of x equal to 0 and try to solve for x. That should give us the x-intercepts of this guy. We'll do the same thing because it's got 4 terms just like the last one. We'll split it down the middle and factor out what's common. Between the first and the second terms here, x squared is common between them. And if I factor x squared out, x plus 2 is left. Okay, and then between the third and the fourth terms, they don't really have anything in common, but I do have to factor something out. So I'm going to factor a 1 out, but like we said, whatever sign you see in the middle should be the sign that you factor out. So since this was a minus, I'm factoring a -1 out, not just a 1. So I guess keep that in mind on these, that you need to factor something out. If you don't see anything in common, everything always has a 1 in common, because 1 divides into anything. So it looks like I'm doing a good job because x plus 2 is the same in both parentheses. So I'm going to factor that out, x plus 2, and then the leftovers go in the second parentheses, the x squared and the -1, you know, from here and here. And then it just so happens, I think they did this on purpose, but that x squared minus 1 is another difference of squares. So it should factor into 2 smaller linear factors. It should be x minus 1, x plus 1, or vice versa. And now we're going to use the zero product property. I'm going to take each of those factors, x plus 2, set him equal to 0, x minus 1, set him equal to 0, and x plus 1, he gets equal to 0 too. And we'll solve all those guys, and those will be our x-intercepts. We'll go -2 here. That gives me -2 as one x-intercept. The next one I'll add 1. So I get +1 as my next x-intercept. And then I subtract 1. That gives me -1. This time those are all unique. None of those are repeats of the others. So I'm going to list all of them. My x-intercepts are x equals -2, x equals 1, and x equals -1. And those can be in any order. You don't really have to write those in any certain order. There we go. Oops, why'd I cross that off? Beautiful. Alright, so this section kind of has a lot going on. I'm sorry, it's a lot to remember. But let's see, the next objective, which is not even the last one, there's plenty here to offer. It says, find the zeros of this crazy function, and then give the multiplicity of each zero. So that's where it comes in, where, remember I said, the number of times that a zero occurs actually matters. So I'm going to write that out. The multiplicity of a zero is the number of times that zero occurs in the factorization. The easy way to think of it, though, is it'll be the exponent on that factor. It will be the exponent on that factor. So that's the definition of multiplicity, but I'm going to write what, I guess, the significance of what multiplicity is. What does that mean as far as the graph goes? So, for one thing, if the multiplicity of a zero, or x-intercept, remember that's the same thing, is odd, so it's an odd number, the graph crosses the x-axis at that value. And we'll kind of draw a picture of it so we can kind of see the difference. If the multiplicity of a 0 is even, the graph touches the x-axis. That's how they phrase it, right? Yeah. Touches the x-axis and turns around. That's what they say. Touches the x-axis and turns around. Sorry, this is taking up so much room. Alright, anyway. So maybe we could draw, yeah, let's draw a picture of that. I'm going to take up a little room on the next example, but whatever. We'll make up for it. So let's see. Let's draw a cute little graph here. How about on the left side he goes and just touches the x-axis, but then he comes back up and bounces off of it. But on the right side of the x-axis, or sorry, on the right side of the y-axis, he's going to go through and then back up through like that, something like that. So let's see, this x-intercept here, you know, it is an x-intercept because it hits the x-axis, but this would be an even multiplicity intercept because it bounces. It touches the x-axis, but it comes back up. But the other two x-intercepts they must be odd multiplicity. Odd. And this graph I just made up just now, so it's not like I got this from anywhere. Just a visual way to see it. Multiplicity. And that's because the graph goes straight through those x-intercepts. It doesn't just touch and then come back up. Alright, so we're supposed to determine from the function given whether it's going to be what kind of multiplicity each 0 has, and then whether it's going to be touching or crossing the x-axis. Let me try to write that function lower so I can work on it. What is it? F of x equals -4 times x plus 1/2 squared times x minus 5 cubed. Okay, there it is. So if they want me to find the x-intercepts, I'm going to, like we did before, set this equal to 0 and solve for x. In the last example, though, we had to actually factor it. In this example, it's already factored for me, so that's one good thing. So I could set each factor equal to 0. First of all, the -4 you could disregard, because if I try to set that equal to 0, you're not going to get any solution out of that. There's no way. Okay, so don't worry about that. But the x plus 1/2 squared, I can set him equal to 0, and the same thing with the x minus 5 cubed. So the x plus 1/2 squared, let me see, I'll square root both sides, and then to get rid of the square. So I have x plus 1/2, and you know, I'm supposed to put plus or minus 0, but plus or minus 0, that doesn't mean anything, because 0 is already, you know, it's not positive or negative. And then the last step would be move the half over. So it looks like -1/2 is 1, 0. The other one I'll get from the x minus 5 cubed over here. I need to get rid of that cube in order to solve this, so I'm going to need to cube root both sides. And as we've seen before, a cube root does not produce a plus or minus, so I don't have to worry about that. It'll cancel the cube on the left just to leave the x minus 5, and then the cube root of 0 is 0. And then I'll solve it by adding 5 to both sides. So there's our other x-intercept. We have 2 x-intercepts here. Alright, so what we're trying to do is figure out the multiplicity. Multiplicity, okay, of the first one that we found, the -1/2. All I really have to do is, kind of like we described, is I'm just going to go back to the factored form and look at the exponent on that guy. So that 2 that I just highlighted is the multiplicity here. So that's why x equals -1/2 has multiplicity 2. And let's do the same thing for the x equals 5. Let me go back to the factored form. Here he is, and then look at the exponent on that factor. It's a 3, so that means multiplicity is 3 for that guy. Multiplicity is 3. Okay, so we kind of know now, sort of, how to find the multiplicity. It's just wherever that 0 came from, the factored form, what was the exponent on that factor? And then the other part was this guy here. It says, if the multiplicity of a 0 or x-intercept is odd, the graph crosses the x-axis at that value, but if the multiplicity is even, the graph touches. So one of these is odd, one of these is even. This guy's an even number, since 2 is even, so it touches the x-axis at x equals -1/2, but it won't cross it. And since this guy's multiplicity is 3, which is odd, it'll cross the x-axis there. Axis at x equals 5. I know this especially this example seems like a lot of work, but you know, a lot of the time I spent on this example was writing down this explanation, but at a certain point that'll be all memorized in your head. And then if you think about it, all this stuff you could have done in your head, because, well, you know, if you get really good, like, I know that 1, 0 is going to come from this guy, and I could just kind of picture, if I set that, what I just highlighted in purple or pink or whatever, if I set that equal to 0 and solve for x, I'm going to get -1/2. So there it is. And then I say, okay, what's the exponent on that guy? It's a 2. A 2 is even, so it has multiplicity 2. Even multiplicity means it touches the x-axis, but it doesn't go through. Okay, bam, there's my answer. And for the other 0, I'm going to look at x minus 5 in the parentheses. I imagine if I set that equal to 0 and I solve for x, I'd get +5. So I know the x-intercept. Its multiplicity is the power, so 3. 3 is an odd number, and an odd multiplicity means that you're going to cross the x-axis there. So yeah, like I said, a lot of this extra writing I did was just because, well, this is our first time doing it, so we got to be careful. But I think actually this next one, it'll be pretty simple. Let me see. This guy. So I know 1, 0 is going to come from this factor, x minus 3. I'm going to set that equal to 0. And you can actually do that in your head, like I said. You could just set that equal to 0 in your head. Yeah, and then solve it in your head. So the x minus 3, I'm just going to add 3 to both sides. There's one guy. And I might as well say it right now. His multiplicity is only 1. That's because there's an invisible 1 power on that factor of x minus 3. That's an odd number, which means that the graph crosses the x-axis at that x value. Crosses the x-axis at x equals 3. So now we'll do the same for the other x-intercept. I gotta find it by solving this guy. X plus 6 equals cube root of 0 is 0. If I move the 6 over, I get -6. So there he is. The multiplicity, though, is 3 because that's the exponent on that factor, x plus 6 to the third. But that's also an odd number, so it's still going to cross the x-axis at this x value also. The graph crosses at, crosses the x-axis. X-axis at x equals -6. Yeah, so that one was a lot easier, huh? Just a lot of math gets easier the more you do it. Whew, this section has a lot packed into it, so sorry about that ahead of time. Ugh. But I think things will be smoother after this section. This section has a lot. Ugh. Okay, the next objective. This one, okay, honestly, this objective's kind of out of left field, and you'll never see this crap again until you get to calculus. So they're just throwing this in there. They're saying, hey, you know, in calculus, we'll revisit this whole thing, and you'll do this whole, what they call intermediate value theorem. I know, but we won't use it ever again in this class, calculus. But it's just, I guess, like we've seen a million times before. If you've seen it once, when you get to calculus, it'll be easier. Is their idea, I guess. All right. So let's see. Now we're talking about this intermediate value theorem. It says if, oops, I don't know if it got cut off just for this video or for the whole notes, but okay. Anyway, it should say if f of x is a continuous function on the interval bracket a comma b bracket, and capital N is any number. Oh, that should say between. Sorry, I don't know how that got cut off. F of a and f of b. You know, at this point I'm already lost. I don't know what the hell you're talking about. Where f of a does not equal f of b, then there is a number c in, oh, I should say, the interval a comma b, such that f of c equals n. It's like, what the hell? What the hell are we talking about here, you guys? And I think some things got cut off from this graph. Sorry, here, this is f of a is the y value for the highest point. This is capital N is that middle value, and then f of b should be this lowest y value on the y-axis. Sorry, I don't know how that got cut off. Okay. Let me decode this. It's the statement is very confusing. Oh, actually, this kind of talks about it a little bit here. Let's see if that makes sense. This is just kind of a rephrasing in actual terms maybe we can understand. So if the graph of a function can be traced continuously from one point to another, so they just call it a, f of a, so there's that top point, the top left. Okay, there's one point. If it traced continually to b, f of b, so they're just saying you didn't pick up your pencil and put it back down to draw this graph, it should be continuous, then it must take on every intermediate value from f of a to f of b, possibly more than once even along the way. So it's like, yeah, I guess it's saying n is just any value between f of a and f of b, so just some y value in the middle. Well, for sure there was some x value, in this case we're calling it c, where if I plug c into the function I'll get n. Oops, there you go. Yeah. So and then n, yeah, it's just a general y value, but I could pick any y value. Let's say I like this guy better. Call this, I don't know, what's another letter? M? Capital M? So if I wanted it to cross at m, I could just trace it to the graph, and I know for sure that it's gonna pass that y value somewhere. I just gotta say, well, it passes at some x value here, I don't know. Yeah, so that's all it's saying. It's saying if you take any 2 points on a polynomial's graph, it should be continuous. So that means that any y value I can think of between the two that I've outlined, that should be on the graph as well. That's pretty much it. Yeah, it's like, I don't know, that's kind of a lot, there's kind of a lot going on in that graph, but let me, just to kind of draw a picture, like, I don't know, and it doesn't have to be looking like that, it could look like this more. Like that. So here's a, f of a, that's 1 point, and then here's b, f of b, okay. And then there's some y value that I like that's somewhere in the middle, like, I don't know. Let's say here's the y-axis. And here's the x-axis. Alright, let's say I like this y value. It's a nice one, you know, it's kind of cute, it's not too big, it's not too small, cute little guy. And then there will be a certain point on the graph that has that y value. This is some kind of x value. I don't know what it is, I guess I could find it by tracing it to the x-axis, but yeah, that's just all it is. It's okay. The usefulness of it is kind of hard to tell in this class, but I think in calculus you'll see more of the usefulness. They want us to show that the polynomial function has a real zero between -3 and -2. And that, it's not obvious what to do there, but all we have to do is evaluate the function at those x values. X equals -3 and x equals 2. So we'll do that first, and then I think it'll be more clear how to show what they're wanting us to show. Evaluate f of -3, I'll figure that out. And then f of -2. Alright, let's see. That means I'm just going to plug -3 into this guy. 3 times -3 cubed minus 10 times -3 plus 9. And then I'm doing the same thing for -2. That's the other x value they mentioned. Let's see here. -2. I'll plug -3 in, and then I'll plug -2 in. And I think it'll be, like I said, more clear what to do. -2, okay. Let's see what the hell's going on here. This is 3 times, let's see, -3 to the third is -27. -10 times -3 is 30. Okay, so what the hell's that? 3 times -27 is -81, I think? Does that sound right? Yeah, I think so. -81 plus 30 plus 9. Oh, I gotta think about that. Okay, I think it's -42. Is that right? Does that seem right? Yeah, okay, I think so. Alright, and then let's simplify f of -2. We got 3 times, let's see, -2 to the third is -8. And then -10 times -2 is 20 plus 9. This is -24 plus 20 plus 9. I think that's 5. Yeah, 5. Okay. So that means, okay, this, let's put this all together. That means the graph passes through the points, okay. So we just found that the x value of -3 corresponds to a y value of -42. And then the other point we found, the x value of -2 corresponds to a y value of 5. So notice that one of those is above the x-axis and one is below the x-axis. So I don't know, you don't have to write that down, but if that helps when you look back later. One above the x-axis, one below. So pretty much the argument is, well, a polynomial is a constant function, or no, sorry, not constant function, a continuous function. So if I was below the x-axis, but I went above it eventually, I must have crossed the x-axis to get there. So the graph must have crossed the x-axis somewhere between those two x values, between x equals -3 and x equals -2. And I think the key words that they probably want to hear is because the graph is continuous. Because the graph is continuous. Because we've talked about that before, that polynomials graphs are always continuous. Yeah. Ugh. So like I said, that one, I mean, you just kind of bear with me for these homework problems, but after you do those couple homework problems, you'll never see this crap again. So the next one, they're going to want us to do the same thing. Show that the polynomial function has a real zero between -1 and 0. So what I'm expecting is I'm going to substitute each of those x values into this function. I'll do f of -1 and f of 0. Oops. One of those is going to be a positive number, one of those is going to be a negative number, meaning that one of those points is above the x-axis, one is below. You know, and then that would show that it has to cross somewhere from one to the other. Alright, let's substitute those guys in. The first one they gave me was -1. Okay, -1, I'll substitute that in. See what I get. Let's see. That'll be 2 times -1 to the 4th is +1. And then -4 times -1 squared is +1. Okay, and then +1. So this is 2 minus 4 plus 1. That's going to be -1. Alright, now we'll find the other guy. I'm expecting it to be a positive number because the one I just found was negative. The other x value they gave me was 0 here. So I'll substitute 0 in the function. Let's see. 2 times 0 to the 4th, well 0 to the 4th is 0. Minus 4 times 0 to the 2nd power is 0. 2 times 0 is 0. 4 times 0 is 0. Plus 1 will just be 1. That's true. So one's positive, one's negative. That means, okay, what that tells me is the graph passes through the points I just found. The x values they gave me were -1 and 0. And the y values I found corresponding to them were -1 and 1 respectively. So that kind of the key is that one is below the x-axis and one is above the x-axis. And of course you can phrase this a different way if you think of a better way to phrase it, because I'm not really good at that. And one above. So the graph must pass through the x-axis. Pass through the x-axis between those x values that they gave me, -1 and 0, because polynomials graphs are continuous. You know, or something to that effect. It don't have to be as long-winded as me, or you can make it even more long-winded if you wanted to. But that's the idea. So that was kind of a tough one to wrap our minds around. This next one's not that difficult, so that's good. It's one of our last objectives, huh? Okay, good. Yeah, alright, good. Let's see. And I think the very last objective kind of brings everything together in one harmonious part. So we'll kind of put everything together here. But anyway, this is not quite there. So now we're talking about this number of turning points idea. So what does it say? Let's see. It says, if f of x is a polynomial of degree n, okay, then the graph of f has at most n minus 1 turning points. So okay, n minus 1, I guess that means, like, let's say, for example, your degree of your polynomial is 10. So it's a really high-powered polynomial. A 10th power, that means the number of turning points can't be more than 9. It can't be more than, 1 less than your degree, if that makes any sense. Yeah, and that's kind of because, like, I don't know. Well, we'll see why later. But let's see, just to practice it. Let's see, 7a says, if a polynomial function f is of degree 5, so that means n equals 5 in this case, what is the greatest number of turning points on its graph? So okay, I guess I could say the number of turning points is less than or equal to, because it says it's at most blah. It's supposed to be n minus 1, so less than or equal to n, we said in this case is 5 because that's the degree we were given. So 4. So the number of turning points must be less than or equal to 4. It's either 4, 3, 2, 1, or 0. So let's try to do that again over here. I mean, yeah, once you do one of these, you kind of get the hang of it. So this polynomial now they're saying is degree 4. So that's n. That means the number of turning points, okay, must be less than or equal to n minus 1, but my n is 4. So it must be less than or equal to 3. So it's either 1, 2, or 3. The greatest, okay. So I guess the greatest number of turning points is 3 here. The greatest number of turning points is 4 there. That one's not so bad. That's kind of the last idea. Now we're going to put it all together in this last objective. So it says we want to graph polynomial functions. Now we're finally doing a fun thing. Okay. So let's see. Let's start with this guy here. F of x equals x cubed minus 3x squared. They say now use the 5-step strategy, which they're kind of outlining for us in the first one, but after that we're on our own. We kind of have to memorize the steps. The first one though is the end behavior, so we got to really dig deep till, what was it? It's almost an hour ago now because we've been doing this video for almost an hour. End behavior, let's see. Remember we do that by determining the degree of this polynomial. Well, the highest power I see is 3. So remember that means it's either this kind of cubic shape or the reflection of a cubic shape. But the leading coefficient should narrow it down. Leading coefficient is positive 1 because that's the number that's in front of x cubed. Alright, that means that it must be more like the regular cubic shape because the negative would be required to make it the other cubic shape. So it goes down on the left, up on the right is kind of a description of the end behavior. Or they might say it falls on the left and it rises on the right or whatever. We know what we mean by this, right? Alright, then they want us to find the x-intercepts like we've done before by setting f of x equal to 0. Okay, the function that we were given was x cubed minus 3x squared. I'm setting that equal to 0. And at this point, we should be able to factor this. All the problems they give you in this section, if they want you to find x-intercepts, or they want you to graph it like we're about to, you should be able to factor these guys. So it looks like there's only 2 terms here and they have an x squared in common. If I factor that x squared out, x minus 3 is left. Now I can set each of these factors equal to 0 and solve for x separately. So okay, the one on the left I can solve by taking the square root of both sides. But we know by now that if I square root 0, I just get 0. I'm not going to have to put plus or minus. If it was any other number other than 0, I would, but in this case I don't have to. So I got 0 as one x-intercept, and the other guy, if I add 3 to both sides, I've got 3. Okay, those are my x-intercepts. That's good. Alright, and then it doesn't say it now, but we do want to use the multiplicity to figure out whether these, what's it called? Whether these cross the x-axis or touch the x-axis. So yeah, they didn't really mention that, but we should do that. X equals 0, he came from this factor here. So he has multiplicity 2, which is even. So the graph is going to touch the x-axis but not pass through. Graph. And this could, this part, the green writing that I'm writing right now, this could all just be happening in your head. You don't actually have to write this out. But, this way if you look back, you kind of know what the heck happened. Graph will touch the x-axis at that x-intercept, x equals 0, but won't cross. Okay, so that's really what we need to help us with the graph as far as x-intercepts go. And this guy though, x equals 3, I look back at the factored form, here it is right here. There was only, there was an invisible 1 power on that factor. There was only one factor of x minus 3. So the multiplicity is 1, which is an odd number. So that means that the graph crosses the x-axis at x equals 3. All right, there we go. So we're going to keep that in mind for when we graph this thing. The next step is to find the y-intercept, which we haven't done yet, I don't think, but it's so simple that I guess we could just figure it out right now. The y-intercept you can find by computing f of 0. Well, f of x was, what was it? X cubed minus 2x squared, right? Was that the guy? Yeah, okay. So yeah, the y-intercept should be f of 0. I'm just going to put a 0 in for x. There he is, and I get 0. Looks like I put 0 in for x, I got 0 for y. There's the y-intercept. That's where it hits the y-axis. And then if possible, use symmetry to draw the graph. So this is where you would have to dig back deep in your brain into chapter 2, where we did, is this an even function, odd, or neither? This is where you have to replace x with negative x and see what happens and all that. This one actually happens to be neither. It's not even or odd, so there's no symmetry. No symmetry. Sad. Sometimes that symmetry helps you graph it, but a lot of these won't have symmetry at all. Alright, so let's see what we got. What do we do? The end behavior is, what do we say? Down on the left, up on the right. So I'm not sure exactly what this looks like, but I know it's going to end up going down this way. That way I kind of know at least what happens at the end. And then up on the right. So I just gotta, now I gotta nail down what's going on between those two arrows. Step 2 though is to find the x-intercepts. They're at 0. X equals 0 is right at the origin. And then x equals 3, where's that guy? He's right here. Alright. And then I gotta keep in mind it's supposed to touch at x equals 0 but not cross. But it is supposed to cross at 3. And then I'm supposed to, from step 3, the y-intercept is 0, 0, but okay, I already have that point. That was an x-intercept I found. What a freaking waste of time. Am I right? Okay. So I think the way I go about this is, now that you've plotted all your x-intercepts and y-intercepts, there's only 2 of them, it's not that exciting. I would go from left to right, so I know that on the very left it's supposed to be starting with this arrow. So I start here, and then the next thing that I see on as far as the graph goes is this x-intercept at x equals 0. So I must go upward from this arrow. I know it looks like that to begin with. The first thing it's got to do is hit that x-intercept for sure. Because if there was any other x-intercepts or y-intercepts, I would have found them using algebra, but I haven't found any. Alright, now that I've hit that x-intercept, and then I think about the multiplicity and whether it's going to cross or touch. This one it said it touches but doesn't cross, so I must kind of... I remember my pre-calc instructor talked about... She didn't say touch or cross, she said bounce. So somehow that made it easier for me. I was like, oh, it bounces, you know? So if it doesn't cross, it bounces off. It, like a little, like if you threw a ball on the ground, it bounces. It doesn't go through the floor, of course. And then, okay, now that I know it hits that x-intercept and it comes back down, looking around, the next thing to do is just hit that next x-intercept. So I don't really know where it turns around. You actually narrow that down in calculus. I don't know where it turns around or how low that little dip is that I just drew. But I know it has to turn around to hit that next x-intercept. And that next x-intercept had an odd multiplicity, which means it crosses the x-axis there. It doesn't touch or bounce, it goes through. And then from there, the only thing left to do is connect that line, or that part of the graph with the very rightmost end behavior, which makes it go up forever. So it looks something like that. And I know if yours looks a little different, like if it looks more like that, that's fine too. I mean, mine looks really wide, but you'll kind of narrow down the more specific parts of these graphs when you take calculus. Right now we just kind of care about where it hits the x-axis and whether it bounces or touches and the end behavior, but kind of like I was mentioning, we don't really necessarily right now know how low these dips are. Like this, it looks like it's hitting at y equals -2, but I don't really know if that's right. And in this class we don't really care. We'll figure that out later. That's kind of something more advanced. It'll be easier when you know calculus, if that makes sense. So let's use that 5-step strategy here for this other function, and then we'll be done with this section finally. Sorry, we couldn't keep this video under an hour. Dang it. Okay, end behavior. Let's see. Degree is 4 here, because that's the highest power, which means it's either going to be upward on both sides or downward on both sides. But the leading coefficient, the coefficient of x to the 4th, is 1. That's a positive number. So it's got to be a nice positive parabola where it goes up on both sides. So I know it looks more like that. Okay, up on the left, up on the right. Up on the left, up on right. Okay. Sounds good. And then what was step 2? I think that was the x-intercepts, was it? Let's see. Yeah, x-intercepts, okay. Well, now I'm going to find the x-intercepts by setting the function equal to 0. X to the 4th minus 9x squared equals 0. Alright, so it looks like if I want to factor this, I can factor an x squared out. If I do, I'll be left with x squared minus 9. Let's see, if I set that equal to 0... Well, that's not quite factored all the way, because what's in parentheses is actually the difference of squares. It's x minus 3x plus 3. Alright, now it's factored all the way, I can set each little factor equal to 0. The x squared, the x minus 3, and the x plus 3. So I'll solve the leftmost one by square rooting both sides, and I'll get 0. The middle one I'll solve by adding 3 to both sides, and I'll get 3. The last, or rightmost one I'll solve by subtracting 3 from both sides, and I'll get negative 3. So those will be where it hits the x-axis, but I gotta figure out, is it gonna cross or touch the x-axis at those values? X equals 0 had multiplicity 2, and that's because the factorization part had a second power on it, so maybe I'll highlight it to kind of bring it together. That's where the 2 came from. And that's the significance of the multiplicity, is that just whether it's odd or even, you don't really care if it's 2, 4, 6, 8. All that matters is if it's even or odd. That's an even number. So the graph touches that x-intercept of x equals 0, but does not cross. Okay. Then x equals 3, that guy had multiplicity 1. And that's because there's an invisible 1 power on that factor of x minus 3. That factor only occurred one time, so there's no need to write, to think of it twice. Multiplicity 1, and like I said, it doesn't matter what the multiplicity is, all that really matters is it odd or even. That's an odd number. So the graph crosses at x equals 3. And the very last one I think is going to go similar to the previous one. The x equals negative 3 had multiplicity 1, which is also odd. Also odd. That's the exact same number. And that's because that factor that it came from had an invisible 1 power on it to begin with, too. This guy here, 1, okay. And then that's the same kind of thing. The graph should cross at that x value. Graph should cross at x equals negative 3. Alright, and then I think the next step was the y-intercept, is that right? Let's see. Y-intercept. Step 3. Y-intercept, and that you find by substituting 0 in the function. So it's 0 to the 4th minus, was it 9 times 0 squared? Or was it x to the 4th minus 9x squared? Yeah. Okay, so remember I'm just substituting into x to the 4th minus 9x squared, the original function I was given. Either way, I'm going to get 0 though. So I just found out, oh, the point 0, 0 is on the graph, but I actually, just like the last problem we did, I already knew that because I found the x-intercept to be 0. But I promise the y-intercept isn't always so useless. A lot of times it actually helps you because the y-intercept's different from the x-intercepts. And then what else? What are we trying to do next? I forgot. Step 4 was, symmetry. This guy actually does have symmetry. It's an even, what's it called? Even function. Step 4. Because if you substitute negative x in the function, you get negative x to the 4th minus 9 times negative x squared, which, those are both even powers, so they just swallow up negatives and make them disappear. That's the same as the original function f of x. Replacing an x with a negative x didn't really do much. It just kind of, it didn't do anything. This is the even function. So it has y-axis symmetry. Y-axis symmetry. That could help, that way if you kind of have a bunch of points that you know on one side, but you don't really know what's going on the other side, that would help. So, okay, I think that was it. Were there any more? Oh, then step 5 is draw the graph. Okay. So I just have to plot the the x-intercepts, they were at 0, and then 3 and negative 3. And then if the y-intercept was another unique number, I would actually plot that too, but, you know, the y-intercept's also 0, which is the point we already knew. And then what was the end behavior? Up on both sides, that's right. So, okay, I know it goes up on the left and up on the right. I just got to figure out what goes on in between. But kind of like we did last time, I think what I would do is just go, okay, from left to right, the very leftmost thing that happens is this end behavior that's going up and to the left. Then after that, the very leftmost thing other than that is it has to hit this x-intercept, x equals negative 3. And then once it does that, then I think about multiplicity. So the multiplicity of x equals negative 3, it was an odd number, which we said means it crosses. So I know it's going through. All right, and then I got to think about what to do. Well, it's got to next, from left to right, it's got to hit the next y-intercept, or x-intercept, whatever, this guy. But then from there we said x equals 0 has multiplicity, well, an even multiplicity, which means that it hits that x-intercept, but it bounces off and then goes back downward. So, okay, it goes down. And then I think it's pretty clear what to do next. The next thing would be this last x-intercept. It's got to turn around somewhere and hit that. But like I said in the last one, we don't really know how high or how low these little valleys are. Those, don't really worry about it in this class. We'll worry about that later. That's something that's too hard to nail down right now, but it'll be easier later when we have a lot more math under our belts. But after that, the only thing left to do is just cross it because it has odd multiplicity and then go and finish it off with the last part of the end behavior. So it's pretty much like a W shape, this guy right here. Oh man. So we'll do more of those in coming sections. That was a lot to take in, you know, a lot to memorize. But graphs of polynomials are very complicated. Ugh. So thank you for listening. I'll talk to you in the next video. Good times had by all, of course.